ACAN are pleased to be hosting our 17th event on building with natural materials, focusing this time on designing ground floors with natural materials. We've got some great minds from across industry presenting tonight, followed by a panel session where the speakers will be able to answer your questions posted in the chat box. So I'd like to introduce Nigel Jervis from Team Lime. Nigel will show us how to build limecrete and foam glass floors. Then we will move on to traditional suspended timber floors and retrofit designs with Chris Brookman from Back to Earth. We will welcome next Tasha Greenfield from Natural Building Systems. Tasha will present how prefabrication can be used for floor build-ups. Then Will Stanek from the Hemp Block Company will share his knowledge on building with hemp and lime. And finally, Jeffrey Hart, the earth and floor specialist, will show us how to build with earth today. Before we kick off, I'm sure most of you already know about ACAN, but for the benefit of others in the room, I'll give you a brief introduction into who we are and what we do. So for anyone new to ACAN, we are an open voluntary network of individuals in the built environment industry. Formed in April 2019, it has now grown into a global network of over 3,000 people. It started with a vision for how we could work autonomously as a collective of individuals in order to make rapid decisions and respond quickly to the climate emergency. Our manifesto has three overarching aims: decarbonize now, ecological regeneration, and cultural transformation. You can read a bit more about details about these here and on the ACAN website. ACAN is made up of 10 main thematic groups, of which natural materials is one. Each group is made up of individuals who want to make change happen, and a few people from each group take on a coordination role to help facilitate the group and any actions. You can hear more about what else is going on in the other groups by joining ACAN, and we'll share a link to the other groups in the chat box. I'll now hand over to Steph to introduce the speakers.
Great, thank you, Aurora. Hello, everybody. So on to it, we're going to introduce Nigel Jervis from Team Hour, who's our first speaker of the evening. Nigel's founder and technical director of Team Hour Lime, an award-winning business based in the heart of rural Wales. Established almost 30 years ago, through Nigel's passion and experience, Team Hour has become a market leader in the innovation, manufacture and distribution of environmentally friendly and traditional building materials, as well as the retrofit insulation systems to projects all over the UK. Over to you, Nigel.
Thank you very much, everybody. Thank you very much for the invite. I thought, first of all, it's just worth pointing out what we need to consider when we're replacing floors. There's with whatever we do, we're always looking at condition of building first of all. So the state of the building itself, whether it's in a fit state, obviously all there's protections of gutters and downpipes, land drains around the building, which will maintain an environment which is dry, bearing in mind that a building is sort of 30% more energy efficient if it's dry. So before considering doing any insulation, get it to a fit state. And is what we've been doing for 50 years is actually trying to stop water, and the whole basis of this system, and in fact anything that we do to buildings, is sort of about not stopping it from getting in, which means the water can get out again. So you're creating a robust environment. So, that's the one where I was looking at. Oh, that might have been out of sequence, I guess. So floors. Here it states they're sort of responsible for 15% of heat loss. I'm always a little bit dubious about that. I mean, it depends what the state of the floor is. Lots of floors are obviously sitting on damp soil, and as such, it's going to be fairly inefficient and sucking a huge amount of energy out of the building. So I think it's obviously in retrofit, which we're sort of predominantly talking about. We do new floors as well, but most of it is retrofit. And often we're more limited with what we can do on walls because of cultural and significance of buildings. So we often can't do much with the walls. So we have to look at floors and roofs, I think, to boost it. So the whole system relies on managing water. So the whole system is incredibly simple, and it's simple because of the multifunctionality of this layer, which is clay core. So this bit here is insulation, it's hardcore, it's moisture management. That's insulation there, and from there up, it's thermal mass with whatever you put on top of the floor. So, being incredibly light, you have a great advantage with moving it around. This is between 90 and 150 kilos per cubic meter, so 2 people can move it around. If you consider that hardcore is 1.6 tons to the cube, then you've got a huge amount of reduction in energy to move it both through roads but also through the building. So it's very simple to install. It's got high compressive strength, which means that it acts as a hardcore, so that it will take that, give that structural layer as a hardcore provides. It's also got a thermal capacity of 0.078, which means we can design these floors to give a thermal performance of whatever you want, bearing in mind the restrictions of limitations of depth of dig. And it's made from 100% recycled glass, so it's glass that's it's the majority of glass goes back as glass cullet, but then the waste from that can actually be put in a foaming oven and produces the primary product is a board, and then the secondary product, which is produced from trimming up the boards, is this gravel. And it's non-capillary active, which means that if it's laid at over 100 mil, then that's a capillary break, and so the moisture can't be drawn up from below. So these are its sort of benefits: with a high compressive strength, rodent resistant, easy to process, doesn't deteriorate with age, draining, resistance to freeze and thaw, 100% recycled, acid and alkali resistant, non-combustible, and as I said, a recycled material. So this is actually one of the floors we've laid at our own place, but I think is what's often not looked at enough really is the condition of the building. As I said earlier, it's getting the building to a suitable state. So many projects that we get involved in, people say there's a bit of damp, so they feel they have to put a membrane in. The problem is membranes potentially only cover up the effect rather than treat the cause, and I think that the majority of work that needs to be done is before you get to this stage, and as I said, is making sure that that building is healthy, making sure your gutters and downpipes are functioning, making sure that the land drain is giving that protection around the building, so gravity can manage that rather than having to do something inside. So the idea is you excavate the floor to the required depth, and that depth is determined by heat loss calculation that we do. You then excavate to an appropriate level, making sure that the ground is well compacted. Geotextile going in here. There are certain situations where we sometimes don't introduce a geotextile, which is quite nice because it's not a fabric you necessarily want to use too much of. But the idea is if mortar starts coming up through it, then that the geotextile acts as a filter, so it stops any silt coming into that area. The clay pore's then taken in, raked out, leveled, And as you can see here, you get it to a nice even consistency across the floor, making sure that you're 30% over, because then it's compacted. A whacker plate's run over the top and hunkers it all down into position, and you can see from that shot on the right that the particles, the pieces of clay pour itself, are very sharp, they're very angular, as a normal hardcore is. So they actually lock in together and they create a very stable foundation. And it's you can feel this as you come up through the process of laying it. You go from a material which rocks around a little bit, you compact it, and it makes it gives it a very firm structural base. If you look at each of these processes, from the excavation, laying the geotextile, bringing hardcore in, compacting it, it is identical to laying a hardcore. There's nothing different to that whole process, other than the fact it's an awful lot lighter material to move around. We always suggest that people consider putting underfloor heating in. One of the main purposes of doing this is to reduce the running costs, reduce the load, the demand for heat. So providing an adequate level of insulation below keeps the heat where you want it, and then a slab sitting on top, and that slab obviously is useful as thermal mass. So putting heating in the slab, I think, is a very good idea, because you often are more limited with running pipe works through the building to provide radiator space. And I think that slab heating across the whole surface of the floor gives a much greater even distribution of heat. And obviously that is then you're able to run that on a ground source or air source heat pump. So potentially it's a low-embodied fuel source. You can see around the edge on the left-hand side of the picture, the brown line, that's cork. So that's edge insulation, which is put against the wall, which the slab then butts up against. And that obviously limits the amount of heat going onto the wall, so it's retained within the wall itself. As with laying hardcore, laying a limecrete slab is pretty much identical to laying a concrete slab. So it's a combination of aggregate and binder. We, in general, use an NHL5, which is the strongest of the hydraulic limes. It's often questioned in terms of its breathability. I haven't any evidence to show that that's an issue, and we've done many tests on slabs where they have been saturated for a prolonged period of time, and the moisture has evaporated away without any deterioration to the slab. So I don't have an issue with laying it with an NHL5, but similarly, it could be laid with. You could lay these with a fat lime. The difference would be setting time. It would take a considerably longer period of time and require a good environment which isn't wet or cold to enable that carbonation process to take place and the thing to firm up. You can see on the right-hand side, it's being troweled up to provide a finish. This floor and these three sections of floor next to them were actually all polished. So we did trowel this. If, for instance, the floor was going to be taking slabs, then you certainly wouldn't need to do this floating up, and it would obviously be not as effective if you floated up. You actually want a key, so you want a finger hold and a texture hold for the next layer to go onto it. So it could be just left as a tamped finish rather than floated up, or as on the bottom left-hand side, it's been floated up with a poly float, so you don't draw too many fines to the surface. So Rochester Cathedral, which was a huge floor, it was a massive undertaking, this one, but all went down well until not long after the floor was finished. And there was an enormous flood, and the whole floor was completely submerged. There were a few panicked phone calls. The water drifted back down through the floor, and the whole thing recovered. So it, as I say, it's robust because it's not able to. It doesn't trap anything in there. And if obviously there was a membrane had been installed in this, then it would have been a swimming pool, and it would have been a much greater problem to overcome, probably requiring digging it all up again. Next, please. This is Leicester Cathedral, where Richard III was buried, and obviously a fairly sensitive site. So it helped create a good environment for where he could be interned again, and that is operating very effectively. So this is just showing a way of laying screeds out. So there's a screed being laid on the floor there with a timber on top of it. Those will act as screeds, and the limecrete would be filled in between. I mean, there are many ways of laying these, setting out scaffold tubes, for instance, which then can be set up and screeded between. Actually setting up screeds with mortar like this, or just doing it with a staff as well. Here you can see day joint, broken edge, left open, and it's then being the next day it would be filled in between, and then the last slide is just the finished floor. I think that's me.
Great, thank you very much, Nigel, and thank you to everyone who's sent in loads of questions for you. So we'll come back at the end and we'll do a Q&A session with everybody on all of the presentations that we've had. So on to the next one. We've got Chris Brookwell from Back to Earth. Hello, Chris. Back to Earth was started in 1995 by Chris and was originally a building company specialising in construction with sustainable materials such as cob and lime. By 2007, the business had morphed into a material supplier, at which point Back to Earth's sole business was supplying sustainable building materials. Back to Earth is committed to providing the highest quality, most energy efficient building materials available to help create the most comfortable and healthy indoor spaces. So over to you, Chris.
I didn't realise you were going to read all that out.
You're welcome.
Thanks for that. Right.
Start with an accolade.
Yeah, that's great. I love it. Okie dokie. Okay, hopefully you can see that.
Yeah,
so I'm going
good.
to talk about suspended floors now. So an existing suspended floors largely, because that's the kind of biggest market. So you lose a huge amount of heat down through uninsulated suspended floors. There is a bit of a possibly misunderstanding in the general population that that heat rises, so the importance of insulating suspended floors is probably missed. Sorry, I've got to move. There we go. But actually, through air movement, you get a lot of air moving down into the floor void underneath the suspended floor, but also transfer through the fabric, conduction through the fabric. So you do lose quite a lot. As Nigel said, it's somewhere between sort of 15 and 20%. Fairly typically. Depending on the type of insulation that you use, you can mitigate that by anything between 60 and 90%. So it depends on the type of insulation and how it's installed, and also whether you need to taper the edges, whether you've got to get over dwarf walls, all these kind of things. So there's various challenges. The biggest challenge really to insulating existing floors is to do with moisture. So moisture that is within the timber, or moisture that gets into the timber structure itself, but also moisture in the air underneath the floor void. And actually a lot of historic floors rely on the ventilation paths that you actually get through sort of into the underfloor void, up through all the air leakage paths through the floor itself and up through the building. Now, as you retrofit buildings, you tend to make them much more airtight, and certainly when you insulate floors, you tend to prevent that air movement. The benefit of that, we've got two benefits. One is not losing all that air in the first place, but also you prevent all the mold spores that are in that sort of very humid, damp environment under the floor from actually coming up into the building and regularly populating your house with mold and fungi spores. So pretty useful. Currently, building regs requires you to leave 150 mil void between your joists. When you're looking at ventilation, you're supposed to leave around about 500 square millimeters per square meter of floor, or 1500 square millimeters per meter of exposed perimeter, whichever's larger. And in terms of exposed perimeter, that is on opposing walls as well, not adjacent walls. So you can't have sort of one on the north face and one on the east face. You have to have one on the north, one on the south, one on the east, one on the west, whichever, but opposing faces. And actually, most existing floors really don't have that level of ventilation. So you've got people build extensions on one side and block up one side, or the ground level rises, or plants grow over the air bricks. So there's an awful lot of floors that are really struggling with ventilation. Part L of the building regs requires you to achieve a U value of 0.7 if you're upgrading your existing floor, or if you have to achieve the improved value, it's 0.25. For new floors, it's 0.18, whether you're putting new floors in as an extension to an existing building or in a new building. Actually, that's pretty easy to achieve, so you actually don't need that much insulation to get to that level. New suspended floors also require a concrete oversight, and that needs to be above external ground level, so you don't create a sump under your floor and fill it with water whenever you get a lot of rain. And that is to prevent moisture evaporation from the soil. So I'm kind of going to go completely against everything that Nigel's just been saying. And in this particular instance, we really do want to prevent evaporation from the soil. That is not at all beneficial for suspended floors. The really interesting thing about suspended floors is their low embodied energy. You're using timber materials, you're using, well, certainly we would recommend the use of wood fiber insulation. So using natural fiber insulations, you're locking up carbon into your floor structure. So what does that look like? So for the last 100 years or so, most floors have been built with, green spot on, with dwarf walls, with woefully undersized joists between, typically. And then in between, you should have somewhere an air brick at one end of that channel and hopefully an air brick at the other. So the next thing you do, and again, this is completely counter to what I just said, is if you've got bare soil under your floor, is to cover it. So you'd lay a layer of sand down, you'd put a DPM over that, and then you put more sand over the top, and that keeps the moisture in the soil. And as I say, we don't want to be releasing that into the underfloor void. The next thing you do for retrofit and for new build, it's quite a good way to install the insulation. You use a breathable membrane up and down between your joists, and that will be fairly tightly bonded using double-sided tape or adhesive on the side of the joists and possibly staples. The other thing you want to do is also go around the perimeter of the floor, so that when you push the insulation in, the insulation doesn't actually touch the brickwork. The brickwork can be quite moist at that level, and the lightweight, certainly if you're using something like wood fibre, you really don't want that in contact with the external walls. So you then put your insulation between, and generally you would then put a vapor control and air tightness layer over the top, which is then bonded to the walls around the perimeter, either taped or glued, to prevent air movement from that underfloor void up into the building. You can also do this from below, so that was an above installation. You can do it from below, so you would have to get underneath and you have to install the vapor control layer first, which goes up and down in between each set of joists, and again you'd glue and or staple sort of close to this top edge and get some tension in it so that the membrane is nice and taut. You push your insulation between, and then you'd from the underside you'd put a breather membrane and then battens perpendicular to the joist to support the insulation. And it's really important to have that membrane. Actually, I'll talk a little bit more about that. In practice, 50 mil of the Sticoflex will actually achieve a U value of about 0.4. So you're miles inside the 0.7 threshold. 100 mil joists are pretty common. So 100 mil will achieve about 0.29. If you need to get to the new build target, it's typically about 200 mil between joists. It depends on the perimeter area ratio, but those are the kind of figures. Although the timbers are thermal bridges, it's actually better not to use wood fibre boards directly below those joists in the floor void without covering them. So we've had various projects where we've grown hand-shaped mold patches on the wood fibre boards, and basically the wood fibre behaves as a growth medium for all the bacteria that are on people's hands. Tends to happen in the summer, so it's not a continuous thing. It tends to be a relatively short-term thing, but nonetheless, it's not a good look. And so anything that you have underneath should be covered with a breather membrane just to slow the transfer of moisture from the air into the insulation, because wood fibre is very good at absorbing that moisture and buffering that humidity. When you're retrofitting in floors, it's absolutely vital to assess and make sure you've got cross ventilation. As I say, you can't have ventilation just on adjacent walls. It's got to be opposing walls. And also, when you're insulating those floors, you've really got to consider what happens to the dwarf walls. If the ventilation path is sort of between the joists and over the top of those dwarf walls, quite obviously you can't fill the joists fully because it'll prevent the air from moving through. Ventilation needs to be adequate to keep the RH below 80%, which is the threshold for mold growth and timber decay. It can be useful to monitor that particularly if you've got really high water table, if the surrounding ground is very high, if it's very wet, it's very useful to monitor that. The reason the bare soil should be covered is simply because the soil is fantastically good at transporting moisture. Nearly all of it's done through capillary transfer, but bare soil will evaporate off huge amounts of moisture to the point that even dry-looking soil will have a relative humidity above it similar to that above standing water, and you definitely wouldn't want standing water below your floor. So it really is quite important to put that sort of oversight on the ground, and that's something that's been going on for a very long time, certainly the best part of 100 years. And you don't actually get a buildup of moisture underneath that. The ground underneath it will, the humidity will rise, but it's only going to rise to the same humidity as all the ground around it. It doesn't we don't have a pump there pumping water up underneath it. So in this scenario, it certainly isn't an issue. If you can't achieve adequate ventilation, you can fill the entire void. So if you've got, if the void is filled on all sides with other walls and you can't get ventilation through, you can actually pour in, I'm going to blaspheme slightly and say polystyrene beads. I've never used them, but I'm just going to say it. You can also use foam glass, as Nigel was talking about there, for in exactly the same way. The foam glass would be an awful lot better. It's also because of the non-capillary behaviour of it, and also it doesn't soak up any water, which polystyrene beads will do. So if you're working in an area with high humidity or high water tables, you shouldn't do that. If there's no way of ensuring that even that is going to be suitable, then really we'd suggest you switch to solid floors. And again, we would look at something like foam glass. So we would start with bare soil. Sorry, I haven't got any pretty pictures like Nigel's got. We'd have a geotextile membrane, even though that looks like polystyrene, it's supposed to be foam glass. We'd have normally 200, 250 mil thick, something like that. We'd have another layer of geotextile. Over the top of that, you'd have a leveling layer of grit, because actually foam glass, they're quite big chunks of aggregate. It's actually quite difficult to get it absolutely dead flat. So you'd use a grit leveling layer. We would suggest you use either a vapor control layer or a radon barrier, depending on what the ground conditions are. And then over the top of that, we would lay a very thin wood fibre board, and then a tile called lithotherm, which is a precast basalt concrete tile. So it's a bit like storage heater bricks. incredibly dense, pipes in the surface, so they heat the floor finish very, very quickly. But that whole construction is completely dry. There's no mortars which set and can't be reused, so it's completely deconstructible. Therefore, it's completely recyclable. Because it's dry, you don't get issues with evaporation of moisture then affecting internal timber work if you've got to that point in your construction. As Nigel said, foam glass can cope with water and radon. It's quite easy to put in sumps, radon sumps, or water sumps underneath all that to allow drainage and take that water away. And it then connects in very easily with internal wall insulation as well. As actually was quite useful. Nigel was ahead of me because you could see the edge insulation there, the perimeter insulation, which you would then join into with your internal wall insulation. Okay, I'm nearly on time, sorry, 2 minutes over. Just very quickly, there's a couple of useful links. So there's the Bayes guide for retrofitting floor insulation, the Pebble Truss guide as well, which is absolutely fantastic for all sorts of things. On our site, we've got a link there to how to create that solid floor structure I've just mentioned, but also how to insulate your suspended floors from above and below. Sorry about the shameless plug.
Not at all. Thank you very much, Chris. That's great. I really like your graphics, very techy. And those links were really useful. If you could just put them in the chat so that people can kind of copy and paste them, that would be great, because I will be doing that as soon as I introduce the next speaker. And I also want to remind everyone, we've got a talk. We had a talk. Our last talk was on low carbon foundations. So there's been a few questions on foundations. So if you're interested in learning a bit more about that, please visit our YouTube channel because they're all uploaded, kind of backdated up there. So on to our next speaker. We've got Tasha Greenfield from Natural Building Systems. So welcome, Tasha. Tasha's currently studying for her Masters in Architecture and has a keen focus on people-centered, sustainable, zero-carbon design and construction. She's campaigning for rapid decarbonisation of the construction industry. Tasha's the design coordinator at Natural Building Systems, who have created ADEPT, a bio-based, fully adaptable and demountable structural insulated panel system. Tasha's also ambassador for Zero, a group of professionals demanding net carbon negative built environment. So over to you, Tasha.
Hello. Can you see my screen?
Yep, that looks great.
Brilliant. So hello, I'm Tasha, as Stephanie has just said, and I'm from Natural Building Systems. And so we have designed ADEPT, which is a kind of full thermal envelope solution that includes a suspended deck ground floor. And this is ADEPT on screen. So ADEPT is essentially a kit-apart system comprising of walls, floors, and a roof, as well as intermediate floors and internal walls. And it is slotted together using kind of timber pegs, and that's the same whether it's in the ground floor or in the kind of other parts. One of the key features of ADEPT is that it's fully kind of circular. We've designed it with circular economy in mind. I quite like the idea that one day we'll have like an eBay for ADEPT. So you'll be able to build your kind of ground floor or whole house, and then you'd be able to take it apart by removing the timber pegs. ADEPT is kind of fully bio-based, so it sequesters carbon and it stores that from the atmosphere. It's also, because it's fully prefabricated, it's really quick to build when you get on site. So we turn up on site with the kind of parts and they tend to be built pretty quickly. So as I've said, ADEPT is a kind of full system, but today I'll be talking about the ground floor. So the ground floor differs slightly from the rest of the system. So the kind of core insulation material in the rest of the system is hemp sil, which is quite similar to hemp lime, but it's our kind of unique bio-based biocomposite. The ground floor is slightly different, as I said, so it doesn't have that hemp sil biocomposite material, and that's because the ground floor isn't breathable. As Chris pointed out, breathability in ground floors can raise a whole load of issues with radon gases and gases from the natural earth, as well as mold spores and things like that. The ground floor kind of sets the grid of the building. And so ADEPT is designed with kind of material efficiency in mind. And because of that, we tend to try and use a whole sheet of material. So although it's a kind of fully flexible system, we have a kind of standardized approach. And actually using full sheet sizes reduces wastage and therefore reduces cost, as well as the carbon footprint of a building. This is something I can kind of go into more detail on if anyone's interested, but I guess it's more relevant to kind of once you start designing. In terms of the build-up of the ground floors, this is a ground floor build-up that shows a 363 millimeter cassette, which would reach a U value of 0.12, which exceeds residential part L. This component, which is a 2,400 by 600 millimeter component, would store 66.7 kilograms of CO2 per meter squared. The ground floor components have a 15 mil marine plywood base, 25 mil marine plywood sides, and an 18 mil spruce plywood top. And these components tend to be 600 mil wide when they're standard, and they range in length from 2,400 all the way down to 900, depending on different kind of spans that are required. We can also do bespoke components that are lots of funny shapes and sizes, and I'll show you a project later on that has lots of really funny sizes in it. The ground floor components are hung using a French cleat joint, which is also called a split batten joint. And these components are hung off either a kind of what we call a box beam, which is shown in this section, or they could be hung off an LVL beam. So we'd create what we call a ring beam, and then we'd kind of drop those components into place on that. As Chris pointed out, you'd need 150 mil minimum ventilation void underneath the floor. And this is to kind of allow for no kind of moisture buildup. And actually, so we've shown screw piles in all of the kind of details that we've got. And it depends project to project whether you can use screw piles. There has to be kind of adequate drainage. You obviously, as Chris correctly pointed out, don't want your timber kind of floors sitting in moisture. There's also a variation of the floor, which has a kind of flush threshold. So using gabions as a retaining wall, so that you can kind of have that, because it is sometimes required on projects. This is just a table to show the kind of variety in different build-ups. So going all the way from 0.18, which I think is commercial part L, all the way down to 0.1. So from 233 millimeters to 433. Which all seem like very funny numbers. But again, we've designed everything with kind of optimum material efficiency in mind. So getting the most out of the sheet material that we're using, but also the most out of the hemp fiber insulation that we use. So a couple of examples from projects, and I have to apologize. It always seems like when we're on site, we never take very nice photos. And actually, so this is one of the really early projects that we did. And it's the only project that we actually installed the screw piles on ourselves. So we used very small screw piles for this. So we've got a kind of slightly funny video of our site guys installing these. And believe me, it wasn't this quick. The ground is quite hard. These are only a meter deep. On bigger projects that we've done, you use a kind of proper installer, which is a kind of mechanical thing. This is another project. This is a project I was talking about earlier that has a whole load of funny angles. I guess, sorry, just jumping around on this. So what we would do once these screw piles are installed, we would install the kind of ring beam, and then we drop the cassettes in place. So this is the project with all the funny kind of angles. And then this is a slightly funny photograph of that floor. So once we'd installed it, so that was LVL beams that sat directly onto screw piles. And then it was kind of lots of funny shaped cassettes, which were kind of precision engineered to get them to fit. But once we'd got the LVL beams in the right place, the floor components dropped in fairly easily. And then this is that project now. We're on site at the moment. So you can kind of see the void underneath the floor and the fact that it's raised up. And then this is another project that we completed just over the summer, which again has a suspended deck timber floor. And you can see, so it's LVL beams. And then it also has a kind of what I called a box beam earlier as a ring beam all the way around. And that's it from me. Yeah, I'm Tasha. Just shout if you've got any questions.
Brilliant. Thank you, Tasha. There have been a lot of questions in the chat, so yes, keep those coming for the Q&A session later. So we're going to jump to Jeffrey, if that's all right. So yes, please welcome Jeffrey Hart, the natural builder. Jeffrey is host of a incredibly brilliant, if you haven't heard already, podcast called Building Sustainability. And yeah, I recommend everybody go listen to it. It's full of a wealth of kind of amazing guests you've got and speakers and great ideas. Jeffrey's also an earth and floor specialist. He believes in high performance buildings from low technology materials, homes that are healthy to the occupant and the environment, both in construction and in use. And he'll tell you more about that now. So over to you, Jeffrey.
Thank you very much. Crikey, that's slightly, I'm blushing a little bit. Let's get that shared. Can you see that?
Yeah, that is great.
Lovely. Okay, so I'm here to talk about earthen floors. We're going to chat about what is an earthen floor. We're going to talk about the build-ups. We're going to talk about variations that we can do, and we're going to talk about the limitations of an earthen floor. They are pretty specialist, but I think they're worth it. Picture on the right-hand side there is probably where sort of most people would think an earthen floor would go. That was in a Grand Designs house. It's quite wobbly. There wasn't a straight edge in it. Doesn't have to be like that. These are earth floor projects where we came in and just installed a 20 mil top coat of earth over an existing concrete floor in both of these examples. The one on the left is an Enefit cottage, and the one on the right is a, how would you describe that, sort of warehouse workshop space in London that had a complete retrofit. That's got clay on the walls and unfired clay bricks as partition walls. One also thing that people find surprising about earthen floors is that you can use it in a bathroom with correct detailing. So what's in an earthen floor? The binder is clay, and predominantly we will use a bagged clay product, a powdered clay. I've used this photo because we can use site clay. Very often when you're digging foundations, you might dig up clay, and if that's properly stored and kept free of topsoil and contaminants, we can use that to put back in as a floor. So probably the most sort of low miles you could possibly do for a floor. Second ingredient is sand, sharp sand, well graded. And the third ingredient is fiber. Now I've shown straw there. I don't actually use straw very much anymore. You could use any sort of natural fiber. You could probably use other fibers, but I don't, because why would you? So all of those materials are mixed with water in a very specific ratio that is different for every site clay. So if we're using site clay, we need to test what the ratio will be. Site clay from one site to another will be different. So yes, all those materials mixed up with water, and that is then laid. We predominantly do a sort of poured system, very much like Nigel was showing with the limecrete. It's poured and then smoothed out to a sort of polished finish. That is then left to dry. We generally blast it with fans to sort of hurry it along. And then the final ingredient is added. So this is linseed oil, comes from the flax plant. The linseed is soaked into the floor. You go around with a paint roller and roller it on. And the linseed oil will polymerize. That forms long chain molecules, which makes the floor really durable. It makes it waterproof, really changes from a sort of clay plaster material, which is fairly fragile, wouldn't last too long as a floor. Once this has gone in and polymerized, yeah, it's very, very durable. Back in the past, and in various parts of the world, they would use animal blood instead of linseed. Linseed a little more palatable, I guess. So build-ups very much the same as Nigel's with the limecrete. Love using geotext. Sorry, love using geotext. No one loves using geotextile. Love using glaze or foam glass for all of the reasons that Nigel said. Underfloor heating works great with slabs, as Nigel said. We can do here, this is sort of the gold standard in my eyes. It's quite specialist and a bit involved. What we'd like to do is use the earth that's dug out from the foundations. If that's stored, kept dry, free of contaminants, very often we can put that straight back in, compact that down on top of the pipes, and that becomes our subfloor, our base coat, and then we'll come and pour 20 mil of top coat on top, which gets the oil. Quite often, because it's quite hard to convey all of the sort of details of using that earth, and sometimes not all site soils will be suitable to do that. We can actually swap out that base coat layer with MOT. So generally speaking, there's a local MOT supplier, so granite aggregate, that's used in roads. Some of those all around the country, so you can get quite a nice local supply, and that can be installed by a site team. It's as simple as putting some down, whackering it, building up in small layers to aid compaction. So the second one we do quite a lot, and that's if there's an existing concrete or limecrete slab. We can come in and lay a 20 mil top coat on that, as long as the floor is in good condition, there aren't big cracks and things like that. We'd use an electric underfloor heating system in this. You can use water, but we need to build up the height just to get a good thickness of material over the underfloor pipes. This one we do quite a lot for people that never realised that they could have earth all the way through, and they've sort of got halfway through their build and then gone, I want earth, and this happens. It's sort of brown washing, I guess. Finally, earth floors can go on top of suspended timber floors. With this, you just have to be really careful about not having too much deflection. That might mean that you need to beef up existing joists. It might mean you need to add in an extra layer of sheet material, glue and double screw that to remove any sort of flex in the floor. If there is too much flex, it will crack. And that is the exact same specification as if you wanted to tile onto a timber floor, suspended floor. So variations on the poured earthen floor. This actually is a project done by Will Stanix. These are H.G. Matthews strocks. They're laid on a lime mortar with earth mortar in between, and then they're oiled as you would do the sort of standard floor. It won't just work, it will work with any type of cob block. So yeah, you don't just have to use strocks. There is, so on the left, this is again Will's projects. You can see the foam glass strocks being laid on the lime mortar, and you can see the dark brown of the mortar that's going between the clay, so keeping clay touching clay. You can use that as a base to pour a thin top coat of earth on top of. Picture on the right is the 20 mil slices of the clay blocks of the strocks. That is laid on top of a limecrete slab, I believe. Again, not my project, one of Will's. So laid kind of like tiles, and again that will get oiled these two options pretty good if your time is of the essence. You have much sort of smaller drying times, and of course if you prefer that look. So limitations of an earth floor, it is about as hard as a wooden floor. So all the protections that you would do to protect a wood floor, you need to do for an earth floor. So furniture with spiky legs would need little coasters under it, felt pads under, big sort of sofas or things like that. Stilettos would probably cause little pinholes. Yeah, so really anything you do for a timber floor is what you do for an earth floor protection wise. And this is a floor that has just had its coats of oil, which sort of brings up the point of timings. So if once we've laid the floor, we get it drying. So the first stage is it dries, we're just evaporating the water. That usually takes about a week. And then once the oil's gone in, that takes 10 days to polymerize. And the oil is polymerizing at a logarithmic rate. So it goes quite quickly at the beginning and then has a long tail. So it is getting harder and harder as we go. So one of the limitations is that you can't walk on your floor for 3 weeks, which obviously has scheduling complications, I guess. Or things you just need to work around. But is it worth the bother? Using the beam calculator, you can see a sizable reduction in emissions for swapping an earth floor for a concrete floor. That's it. Thank you very much.
Beautiful. Thank you very much, Jeffrey. And if you'd like to put a link to your podcast in the chat, I think everyone would appreciate that. So
Of
if you'd like to know
more.
Shameless plug on your behalf. Okay, so we've got Will Stanix next. Will became the UK's very first hempcrete contractor back in 2008. His early construction experience led him to co-author the Hempcrete book in 2014. Will's designed and constructed his own innovative hempcrete house in 2017, which was a finalist in the Structural Timber Awards of that year. So recently, Will's begun producing his own hemp plasters and supplying hempcrete blocks for his new venture, the Hemp Block Company. In his latest pioneering self-build project, Will is set to lead hempcrete down an even more sustainable path as he develops and uses clay as the hempcrete binder throughout the build. Okay, over to you, Will.
Okay, and you can see my presentation, yeah?
Yeah, that is good. Well done.
Oh, phew. I've literally been running around for about an hour. Anyway, so yeah, I'm going to talk about hempcrete floors. I'm going to take you through a few projects step by step. I thought was the best way to illustrate them. And when we talk about hempcrete floors, we're normally talking about a solid floor, and it's not a floor finish. It kind of replaces a floor screed, but it happens in a different part of the build, which is why I'm showing you step by step. You'll see it when it comes in the build amongst the pictures. So this is a project in France, and one of the features of a solid hempcrete floor is that you have a free draining layer beneath the hempcrete. So in this project they use gravel, so it's like a rounded gravel. They're all big lumps, there's no like sand or anything, so that's a free draining layer, but it has to be quite deep to be free draining. So that's the sub base underneath the hempcrete, and then it stays like that for a while. You can see through the doorway that it's still stone whilst the frame goes up and the walls are going up. And then this is the little mixer used. So it's mixed on site in this little mixer and laid as a floor screed on that, which I think was limestone tiles on this build. This one in Finchley started as a hole in the mud, like a lot of builds do. And then you can see we put a layer of hardcore compacted within the building there, and that's kind of how it stays until the walls and the roof are up. So the frame's gone up, and then it's watertight, and the hempcrete's there, and then we can start the floor. So this one, as its free draining layer, uses LECA, or light expanded clay aggregate, and it's the coated leaker, which means it's been coated with something that stops it wicking up moisture. So there's no plastic membranes in any of these floors. They're the free draining layer is kind of your waterproof, and that's leveled as much as you can with these things. It's kind of like a ball pond. And then the hempcrete floor has the timber battens set in because it was having a solid timber floor, so the battens take the timber floor, except for some of it, which is brick laid straight onto lime mortar. This is a extension to a house in London. This is the oldest hempcrete floor I did, which is 15 years old, around about now. So that's just the hardcore beneath it. I haven't put anything in there yet. And on the right, you can see the damp-proof membrane. It goes right down to the hardcore layer. So it's got to come right down to for the full height of the free draining layer, right down to the sub base. So again, this used coated leaker. And there's me getting my battens ready, which just sit within the hempcrete to connect a solid wooden floor to. If you weren't having a solid wooden floor, an earth floor or a stone floor or brick or something else, you wouldn't need these battens. So this is the setup, just a little mixer. And that was the mix on this particular build, which is VCAP prompt natural cement, hemp and the water. So that's the ratio for one mix there. It's roughly 3.5 to 1. So there we go, setting the battens in as I go. So I've done the whole floor. The hempcrete on most of them is around between 100 and 150 mil thick. You wouldn't go less than 100, and you wouldn't really want to go wet cast more than 150 because it would take too long to dry. So I put half of it down, and then the other half I'm doing between the battens as I go. It's just an easier way of doing it. And so this is basically showing you when you're working on it, you might put boards down, and if you pick the boards up and they're wet underneath, that's a sign that the floor's not dry yet. So whilst it's drying, you might work on boards and then just pick them up at the end of the day. But once it's dry, you can just work on it like a normal floor, normal screed, and roll your scaffold tower around. This is not my build. I just did the floor, the earth walls, nothing to do with me. And this is where it was stacked under the stair. And because it was plastic on the floor, it didn't dry properly. You can see a little bit of white mold under there. But once that was removed, once the plastic was removed and the mold was brushed off and it was allowed to dry, it was fine. But it's just, it's something to think about whilst it's drying, which might take 4 or 5 weeks. You can still work on it and walk on it because it's hard, but you just can't keep things on it overnight. You need the air to get to it. And that's the bit of the floor. So this is so we've had extensions and new build, and this is a renovation. This is my own barn. So first of all, stripping the barn back to the timbers. That's just the frame, and then removed all the loose material from the floor, and got some child labour in to compact some hardcore. And then once the hardcore's down, it pretty much stays like that until all the walls and the roof are done. So child labour gets on with the roofing. And then once it's like this, it's all weather tight, can start the floor inside. So this floor uses the Glaypore, the Glaypore, the foam glass, which is compacted with a whacker plate. So all the pipes under the floor need to be set in concrete or limecrete to keep them in place while you're whacking it down, and especially things like the water pipe at the back there, which is quite susceptible. So once you make sure they're all in place, you can put your foam glass in and compact it down and put your geotextile. Oh, if you go back there, you can see the damp-proof course in the walls goes right down to the bottom of that layer. Again, you've got to keep that. If that black damp course down the sides of the brick there wasn't right to the bottom, you could get water tracking through. This is hempcrete block. So obviously hempcrete block is dry, so there's no drying time. And again, I'm setting battens in the floor as I go, because this is a solid timber floor on here. If it was earth floor or tiles or brick, those bits of timber wouldn't be there. So that's all set on a lime mortar, even the timbers. And there's the wooden floor going down. Just screw straight to those battens there. It's not kind of holding it down, it's just kind of holding them all together so they don't move away from each other. And so you've seen blocks and cast, and this is spray application. So this is the spray rig, and it's going on an existing concrete slab in a garden building, which is dry. There's no damp coming through, and so this is being sprayed. So the slab's quite an old slab. This is being sprayed 6 inches thick. So that in front of Jamie's feet there, you can see that bit of timber with a bit of timber screwed to the end like a T. We just spray between that, move it back, spray it more, move it back, spray it more, and scrape it off as we go to give a nice nice level hempcrete floor. So there's no battens in this one. I don't think this build's finished yet. I'm not quite sure what the finish was going to be on top of it. So that was talking about solid floors, but you can do suspended timber floors as well. This is in a B&B in Oxfordshire, and this is one of the upper floors. It's not the ground floor, it's the upper floor, and all the internal walls are hempcrete as well, because the owner lives there and didn't want to hear everybody trundling around. So the downside is it's a lot heavier than other insulations you might put in between the upper floors, but it's very, very soundproof. So they were very pleased with how that turned out. And the other benefit is you can use it underneath as a ceiling to plaster onto. And I'll just give you a little, this is not a floor, but this shows you kind of how it's done. So if you look at that ceiling of this little extension around the roof light there, those battens are going to be holding the hempcrete in. So packing the hempcrete around the battens are perpendicular to the joist. And then when you take the shuttering from underneath, you have a hempcrete ceiling. And obviously if there was a room on top of that, you'd have a hempcrete floor as well. So if you want to look at technical details, if you go to thathempcreteguide.co.uk/downloads, I've got a lot of the binder literature. There's so the brands or the producers of the binder, there's Tradical, there's Batishon, there's VCAT. They publish a little guide which has all the technical details for the floor mixes. So you'll find that in the downloads page there on the left. Then in the middle, that is the picture of one of the VCAT's brochure, and on the right there, it's showing you where it's talking about floors. It gives you little details, drawings, sections, and it tells you the strength of the floor, the mix to use, how much water to put in, and all that kind of stuff. And that is hempcrete floors.
Fab, thank you so much, Will. That's great. And yeah, it's great to see so many you kind of built examples. And could you also put a link in the chat to your downloads? I think that's the second last slide you showed. I think that'd be really useful. And I just want to say thanks to everyone for all the questions that have come in for Will as well. And I'm going to pass over to Tom, who's going to be hosting the Q&A. Thanks everyone for speaking.
There we go. Hi, everyone. Amazing talks, guys. Thank you very much. I've got a big old list of questions for you, handily divided up by speaker. So we're going to go right back to the beginning to Nigel. Yeah, Nigel, are you there? Right, first question, if you can hear me, from Ran. Yeah. Cost comparison, foam glass versus PIR for an overall floor construction. Any thoughts?
Reassuringly expensive. I always find it hard answering this because actually you're comparing completely different things. And I wouldn't use PIR in the builds that we do for a number of reasons. One, I think it generates problems. It generates moisture can sit where you don't want it. It's not a nice material to use. I don't think it works with the structure of the building. But yeah, it's what we're confronted with, that cost comparison. But I think it's balancing out up against longevity and compatibility with the buildings that you're working with, and also the sorts of materials you want to be putting, well, in your body and around your body, which forms part of our set of values.
Totally. Is that something that ever comes up, that you have projects where people are sort of talking about PIR and you're having to make the case for
time? Well, all the time.
Yeah. I mean, that one might be worth anyone else interjecting on. Chris, I'm thinking perhaps.
Thanks, Tom. I was going to say, in terms of sort of the cubic volume, it would be around about, hold on, that's the wrong way around. It's about 135 quid a cube uncompressed. By the time you've compressed it, you lose about sort of 25-30% of the volume. So you're probably looking at about 180 to 200 pound a cube. So what's that? 18 pounds a square meter at 100 mil, or to £6 a meter at 200 mil. So it's not, it's not that expensive. If you take in, well, it isn't expensive at all, actually. If you take into consideration, you've got to put down hardcore and concrete and all the other things that you might use with Celotex, I don't see an additional cost, really.
The actual structure itself, it's because it's doing so many jobs for one application. You put your hardcore in, you've done your moisture control, you've done your insulation, and you've done your hardcore. Yeah. So you have to look at, and going back sort of 20-30 years when we were doing these, the prices were trebled because people didn't understand it. But actually, once you start calculating in the labour saving cost of the installation, then it looks attractive.
I just it was Ran who asked that question, has got his hand up. Do you want to just quickly?
Yeah, I suppose that's what I was fishing for, what Chris was talking about. It's the whole floor build up, that you don't need so much hardcore and all that sort of thing going into it. So I think that's what that's what I'd like to pursue in a job. So I'll take that on.
Fantastic. Right. Yes, and moving on, more foam glass quizzing for you, Nigel. High embodied energy due to the energy consumed during the recycling process. So how sustainable is foam glass factoring in that carbon footprint? I guess versus alternatives.
Yeah, quite. You've always got to look at what the other options are. Yeah, I mean, transportation costs, because this comes from Germany, obviously have to be put into that as well. But it is making use of a material from a waste stream, and as I described earlier, it's the waste from the waste. But I think in terms of carbon, it's probably not looking that bad compared to something like a PIR board.
Okay.
Can I add a bit to that as well? I just answered Andy's question, actually. It's 0.277 kilograms of CO2 per kilo equivalent, because I keep that sort of figure in my head. So relative to something like mineral wool, it would be about a quarter of the embodied energy of that. Relative to plain aggregate, it would be probably 10 times more, but it's not being used as plain aggregate. So as Nigel said, it depends what you're comparing it to and how you incorporate it into the build-up that you're creating. So I wouldn't have said it was a high embodied energy material.
Okie doke. Right. Radon. What can you do in a radon area? And is a limecrete slab suitable? That's Santiago. So that's again Nigel, I guess, or but anyone else can jump in on that.
When radon is radon protection is required, then we put a radon barrier in. We suggest that the radon barrier goes over the top of the glaze pore, so over the top of the geotextile, which sits on the glaze pore. so that the geotextile then protects the radon barrier, and the slab goes on top of that. So if there is water moving around getting in, it could go into the clay pore region, in which case it can disperse. If there's water that sits over the top, then it will sit within a limecrete, which is able to dry out again. But that's the place in which you can put your radon barrier, and as Chris said, sumps can be incorporated within the clay pore region as well.
Cool. And then final one specifically for you, Nigel. Floor finishes on the limecrete. What are the limitations? And what are the, I guess, possibilities as well?
None really. I mean, obviously, if you're putting underfloor heating in, it's a good idea to have something solid, so it contributes to the thermal mass which sat on top. Timber floors can go in. You're obviously reducing to a point the efficiency of the floor, the release of heat from the floor, and the limitations are making sure it's dry. Otherwise, your floorboards are going to pick themselves up and walk out of the building if the floor isn't dry. And generally, we're quoting standard concrete drying time, so a millimetre a day. When you're in a cold, damp bit of the UK in the middle of winter, then those drying times can be extended. But those are things that really you should be taking into account whatever you're doing, and managing the environment. So making sure that it's closed up as much as possible, so it's not getting any wetter. You're encouraging a certain amount of warmth so that it can, and ventilation, so that moisture, so for every ton you put in, you're putting another 300 litres of water in. If you do that in a sealed up building, then it's not going to go very far. So you need to manage that. So, I mean, as with most things that you're doing with building, you actually have to plan it at the right time. And we know how easy it is to get a job on site with the architects and the builders and the clients to all arrive there in the spring, all nice and easy, ready to lay. Maybe.
Yeah. And then, I mean, other finishes that can go on limecrete? Timber. What else?
Yeah, timber, lino. I mean, anything can go on top of it, really. I mean, we from an efficiency point of view, it's, as I said, good to have a bit of thermal mass. We also do polished limecrete floors, and there's a whole sort of variety of those using different aggregates. So it can be polished, or you can, in general, things like flags over the top, because I think the majority of what we get involved in is sort of retrofit, or so flags or tiles would go over the top. Anything that's heavily glazed is obviously going to limit the breathability of the slab. But my feeling is that the efficiency of the floor, the benefit of the floor is done by the management of water that you do around the building before you actually start, and also the whole system has the ability to wick and move moisture around without concentrating it underneath a heavily glazed tile.
Yeah, and I guess one that hasn't come from the group, but it's coming from my head, is or conversations that the natural materials group's been having previously, is about the sort of embodied carbon in lime itself. It's, I mean, not a low embodied carbon material. I don't personally have the numbers in my head. I bet Chris does, for OPC versus an NHL5 versus an NHL 3.5, or versus a fat lime that you mentioned. I mean, is there an advantage from a carbon point of view or others for using an NHL5 limecrete over a sort of an OPC, concrete slab?
I mean, certainly a limecrete slab is much better suited to enable to take moisture on and release it. There is something strange that happens when you walk across a limecrete floor as well. It does feel completely different. It has a different acoustic. It tends to have a sort of softness to it. But in terms of, so I think there are various benefits to laying a limecrete floor as opposed to a concrete floor. I think it gets very complicated, and I'm always very skeptical about people doing those calculations and who does them and how they're done. But certainly firing lime as opposed to concrete, you're firing at a lower temperature. So there's less energy that goes into lime to convert it into a binder than goes into cement.
Right. Cool. I've been told to push on, so I'm going to do exactly that. Right. So I'm going to thanks, Nigel. Might want to interject later with pertinent points, but Chris, we're going to move over to you. A question from Ben: What oversight materials are available other than concrete? I'm not entirely sure I understand
Plastic.
that question. Right.
Yeah, you need something. I don't know of a natural material that you could use in that sort of situation. It is going to be a polythene DPM, as simple as that. If anyone has got another solution, I would be quite open to it. But for cost and practicality, you're not going to go and find anything other than that is readily available, other than a 1000 gauge, 1200 gauge piece of polythene. So
right,
yeah, that's the simplest way to do it.
Despite the fact that the vast majority of timber floors in Britain were built before plastic. What's the story there?
Absolutely. Well, like I said, they were also built before they were insulated. So
exactly,
the process of insulating is changing the conditions completely. So you unfortunately have to change all the conditions completely. Mm-hmm. So
okay, on that one then, talking about other bits of plastic, could a breather membrane below the floor be emitted with a deeper ventilation void, say 300 millimeters?
In theory, it can, but the caveat to that is how you actually monitor the airflow. So in theory, if you had and 300 mil used to be the standard, certainly in Scotland, I think it was, and I'm not sure about England, but certainly in Scotland it used to be. And if you've got correct ventilation, then yes, in theory that would be entirely possible. The reality is that most of the time the air passage through the underfloor void is not particularly tortuous. It'll go sort of in one corner and out the other, and doesn't really carry all the other air out with it. So you tend to get paths which are well ventilated, and a lot of other paths which are very poorly ventilated. So anything's possible if you can monitor it and you're prepared to take the risk. But if I'm advising someone, I probably wouldn't recommend that.
Okay, cool. I think we're gonna push on through just so that we can get as many of these done as possible. Tasha, quickly, where are you? There you are. I'm looking at you on the screen. Are your panel systems passive house tested components?
So we haven't done any kind of projects up to passive house standard, I think, but we have done U value calculations and WIFI analysis and airtightness calculations. So yes, for kind of passive house levels of insulation, both in the ground floor and on the walls, you'd expect kind of deeper buildups, which is pretty standard, of kind of 400 mil in the ground floor and similar in the walls. And then we use an air tightness tape between the components, which we do as standard anyway. So the ground floor is completely airtight and the walls are airtight and vapor open.
Cool. And so this, I mean, you sort of alluded to this there, but have you monitored these panels after assembly, interested to see how they overcome thermal bridges, if any? Like, how has that factored in your monitoring?
Yeah, so again, in the kind of U value calculations that we've done, we've done a lot of R&D, and particularly developing the ground floor. So the ground floor is the only component where the timber goes all the way through. On the walls, it's a 178 mil cassette, and then we wrap it in a rigid wood fiber, or soon to be rigid hemp fiber. So yes, we built a building on the BT Building Research Park, and we have been monitoring that, and we built that nearly a year and a half, 18 months ago. And in terms of the kind of thermal performance, it performs better than the calculations, which I think is always reassuring.
Cool. Nice one. And I think we've just got one more for you at the moment, Tasha. With suspended timber floors on a new structure, mounted on ground screws, can a SIP-style OSB sandwich construction be used with a hemp or wood fibre full fill and a liquid membrane? Oh my God, I'm just reading this. I'm trying to follow along myself. On the underside, right, instead of a membrane and potential rodent mesh needed. Sorry, that's just been copied and pasted.
No, that's fine.
Followed?
Yeah, so I guess because we prefabricate the components and then install them on site, it would be quite hard to get underneath and apply the kind of liquid membrane, I would assume, on the underside of the floor. Is that right, Tom, or am I misunderstanding?
Sorry, I started reading the next question.
Is it the liquid membrane on the underside of the floor?
And a liquid membrane, so hang on, so a SIP-style OSB sandwich construction be used with a hemp or wood fibre full fill and a liquid membrane on the underside instead of a membrane and potential instead of a membrane.
So I would say specifically talking about our system, that would be harder to do. And actually it's easier to install the kind of rodent mesh and DPM and then drop the panels in into kind of the inside of a ring beam, if that makes sense.
Right. Okay.
Yeah.
Right. Cool. I hope whoever asked that question, John, got what he was hoping for there. Sorry, I wasn't following entirely. But Jeffrey, I'm going to quickly move on to you. I'm sorry, I'm just trying to whiz through these before we get to the end here. But Jeffrey, what you mentioned the earth floor in a bathroom application with the correct details. What are the correct details for a bathroom situation?
So correct details. When you apply the linseed oil, the top sort of 10-15 mil gets saturated. So if water can get around the back of the floor and get into the unlinseed oiled, so the sort of raw earth, it would start to soften, or once it got to a certain wetness, there's a better word from that isn't coming to my brain. Yeah, that would soften. So you need to be very careful just to have a seal around the edges, so that, you know, if like your bath splashes over, it's not getting around the back.
Gotcha. That sounds sensible. Right. Okay. Movement and cracking in a 20 mil top coat on a lime or concrete floor. How much could one expect?
None. Why
Fantastic.
would we do it?
Depending on who's installed it.
So there's an assumption always with clay that it cracks. Lots of clay. So if I did a 1-to-1 clay mix, say 1 clay, 1 sand, that's very rich. That would crack. We go much higher up the sand scale to create our earth floors.
Cool. Right. Oils, boiled linseed or raw, and what about tung oil? Linseed or it's linseed and tung oil mix?
Yes. So I normally put a little bit of tung in with the linseed. So tung oil hardens quicker but doesn't set as hard. So you sort of putting a little bit. I'm sort of putting about a quarter tung to 3/4 linseed. The boiled or raw question comes up always. The difference is a 10-day polymerization time for boiled, up, you know, you're talking sort of a month or 2 for raw. If you've got the time, definitely go for raw. Generally people are already put off, or, you know, hard pushed to do a 3-week not walking on the floor.
Mm-hmm. And I mean, and the boiled linseed oil that you're using, do you know if that polymerization process is in fact boiling or heat treatment, or is it generally secatives and sort of the heavy metals that people are actually afeared of?
Yeah, I don't know of any linseed oil company, certainly in the UK, that it's a genuine boiled linseed oil. They are secatives. So yes, there is like trace heavy metal in there.
Right. Okay. And then quickly one more for you, Jeffrey. What's the difference in the mix for the top for a 20mm top coat and against the base coat? What's the difference between those two mixes? Tiffany is keen to try it out in Australia.
Great. Yeah, lots of earth building in Australia. The difference is generally, so because you're compacting the base mix into a confined space, the mix can be a lot sort of looser. You know, you could do it with, I mean, you could technically do it with no clay at all, and it'd just be an aggregate mix, which is sort of what we're doing with the MOT layer. Nice chunky aggregate. Yes, it's the top coat needs to be a very specific ratio, and base coat less specific, but added in dry and compacted. Yeah, does that answer the question?
Yeah, so you've got you can pretty much put anything, it sounds like, for your base coat. That's not quite fair reflection of what you said.
Yeah, not anything, I should say that, but yeah, the sort of the spectrum is much wider, as long as you're putting in drier end material. If you try and put in wet like clay, you'll run into all sorts of problems.
Right. Okay. Good stuff. Right, it's 8:30 already. Sorry guys, but we've just got a few more questions, so I'm going to quickly push through as many of them as I can. So Will, there you are. Hi. If the timbers stay in the hempcrete floor, are you worried about the potential for rot from the moisture? And if it's straight on the ground, it cannot air. If it's straight on the ground, it cannot air. Oh, cannot air is in the verb to air, like suspended floors or upper floors. So that timber straight in the limecrete, problematic? Question mark.
In the no, it's only like an inch batten sitting in the top surface. It doesn't go all the way into the hempcrete, and once the hempcrete, any moisture it would take away from the wood anyway. It's a more it's a spongier material, if you like. So no, it's a difficult one though, because you kind of think hemp on the ground, surely that doesn't work, but it does. And you know, there's not really any vapor. I don't know. I don't think it really breathes downwards. I wouldn't put it on plastic because you may get water there. You know, as long as you're on something free draining. And I've had a flood in the barn actually on the hempcrete blocks. One of the hot water pipes, one of my joints burst, and it was going all night long. I had a massive flood, like massive, and it just dried. You know, obviously it just dried. I left it with fans on in there for a while, and the floor dried. Now it's absolutely fine. But I mean, I used to say put vapor permeable things on the hempcrete like a finish, and I would say not to put things like engineered floorboards with plywood and stuff like that. But actually, that floor that's 15 years old was engineered. What's it called? Engineered floorboards, which are like plywood with a little bit of oak on top, and that's been absolutely fine. And I think the hempcrete is a lot more durable than you think it is, and as long as there's not moisture getting in there, if you've detailed it correctly and you've thought about it, you know, it's pretty much okay. I mean, I always try and put the hempcrete above the outside ground level if that's possible, you know, in case of flooding and stuff, but it doesn't always happen. But I can, you know, it is, you do think, oh, hempcrete on the ground, but actually it's really quite durable.
Cool. Fantastic. And then we were touching on it there, but was there a membrane beneath the hempcrete blocks? Question.
Yeah, so there was a geotextile beneath the hempcrete blocks, which was more of a thing to do with foam glass rather than the hempcrete. Supposed to put it on the foam glass to encapsulate the foam glass. And I don't, when I'm doing buildings that aren't under building regs, like garden offices and stuff like that. But if it's building regs and I've got a detail from the supplier, then I put it in. Otherwise, I'd be a naughty boy. But if I'm doing a garden office, I don't really think they're necessary. And I've certainly put glade pour and other foam glass things in the ground and compacted them and just built straight off them. I mean, you saw in Jeffrey's presentation, the earth block floor I did was just, they were laid on mortar straight on the foam glass. Mm-hmm. It's been there a while.
And just quickly moving on, do the blocks have how do they perform thermally in comparison to the wet hempcrete, given the sort of mortar joints?
I suppose you get a bit of potential. Well, there's no mortar joints in the hempcrete blocks. I laid them on mortar, but I didn't put hemp. I didn't put. But I suppose you could say, potentially they might not be as good because of the joints, but I don't think there's a lot of air movement up and down through a floor, so I wouldn't worry about that. I mean, it'd be minuscule if there was any difference.
Cool. And then this is a question for everyone who's used lime in their conversation. Is the lime burnt and emitting upfront CO2, just like when producing Portland cement? I know the answer to this one. Who wants to talk about that? Nigel, come on, that's you.
Certainly the softer limes, the more pure limes, sort of 90% calcium carbonate, they're burning at lower temperatures, and also they'll sequester the lime, the CO2, the majority of the CO2 that was given off in the burning. As you go up on the lime scale from a pure fat lime through to an NHL2, 3.5 and 5, proportionally there's a reduction in the amount of CO2 that's sequestered because of the initial chemical set. So you have an initial chemical set of sort of 18%, and the remainder of that set would then be a carbonation set in an NHL2. So the softer limes are generally nicer in terms of less embodied energy, lower firing temperature, greater sequestration.
And so just, I guess this goes back to my question, is there any reason one couldn't do a limecrete floor with a fattier lime than the NHL5 that's normally kind of specified?
Time. Same as finishing on floors. I've done the fat limes. It's good we control it, but generally speaking, we're all racing to get the other side of it.
Right, good stuff. Okay, and then really getting close to the end here. But so Leica, has anyone used them? Yes, we have. We've answered that one. Rather than foam glass, but a comparison in the performance or embodied carbon. It was Will. You'd been using that in one of your projects, right?
Yeah, I used to use Leica until I started using foam glass. I don't know the difference in how, embodied energy and that kind of stuff. I mean, the Leica's drop through a kiln. It's clay drop through a kiln, I think, that makes it bubble up like a Malteser. But I know on site the Leica is like a ball pond, so you have to be very, very careful walking on it when you're trying to lay stuff. Whereas the foam glass, once you've
Nigel, do you have a comment?
I think it outperforms. I mean, the early days we were using Leica, yeah. So in terms of its performance thermally, foam glass is better. Its capillary break is also better, and the most important thing is its structural capability.
Yeah,
it's a hardcore. It acts as a hardcore, so it's better compacting. Sorry, something's gone wrong with mine, so I can't see what I do.
Right, cool, thank you. Last one, Irini, flood risk areas. Just any thoughts on how any of these systems work or don't work or fail in a flood risk area? Who might want to have a go at that?
I wouldn't use hempcrete in a flood risk area.
It's funny because we did a hempcrete. All of our workshops are limecrete, and actually we did a hempcrete underneath, and we put a lime, because it's not something you necessarily suggest people do, but we and that's in one part where it does get really regularly flooded, and I've been really surprised how well that performs. But we've been involved over the last few years with various properties that have flooded, and a particular estate where one of their buildings was getting flooded on a regular basis. The owners eventually said, look, to the insurance company, give us the money, they'll do it. We put cork board on the walls, we put hemp plaster over the top of that, which I was slightly dubious about, and we put a limecrete floor. The day before they moved in, this place flooded again. And again, the water just flowed in as it did at Rochester, and it recovered. So being able to create an environment where you don't stop it from getting in, so you enable it to get out. And so many of the buildings we get involved in are like that. But I think one of the really crucial things is we're obsessed with insulation at the moment. Actually, we should be obsessed with building health, get the building healthy first before deciding which way to go with insulation, because we're sort of in that sort of danger zone of actually putting things on top of buildings which actually aren't ready for it. And I think we need to be much more careful about condition and protection around the building.
Yeah, totally. Tasha, did you have anything to comment on flood and your system?
Yeah, well, engineers are always quite dubious about specifying screw piles in high kind of flood risk areas. So I am not sure that I would recommend that you would use a kind of any kind of suspended timber floor in a flood risk area. But actually, in a kind of moisture kind of looking at it from a moisture perspective, actually it's okay if it gets slightly damp as long as it's allowed to dry out. As Nigel said, actually, if you let things dry out, they're okay. It's where you kind of put membranes in and wrap it up so the moisture gets trapped inside. That's where you get the problem.
Cool. Thank you, Tasha. Anyone else want to have a quick comment on that before
can I just say something?
Yeah.
You can't stand by any sort of anecdotal robustness of a system that gets flooded and might dry out again. I don't think it's a sensible thing to do, really. Probably best not to build in a flood risk, but you know, you don't really know the long-term effects if something gets repeatedly flooded. So
yeah, sorry,
sure.
just to clarify what I was saying, I wasn't saying build in a flood risk zone. I was just saying if things get, I guess, damp, it's not necessarily a massive issue. But yeah, no, I agree, I wouldn't recommend it, and I don't think the structural engineers would let us put screw piles in a flood risk zone.
Right, I think
all sorts of other inappropriate buildings in flood risk zones, though, weren't they? It seems to happen.
There's more money in that, though.
Right, I think that's me done. I'm going to hand back over to Aurora.
Yes, thank you, everyone. That was a great conversation and great presentations. Well, thank you, Tom, and thank you to all our speakers. And finally, thank you to everyone for joining tonight. It's been a real pleasure to see so many of you here.